This session is going to be about coffee and dessert, or Java and the Raspberry Pi. So let's have a quick show of hands. Who's heard of the Raspberry Pi? Okay, good. We have the right audience. Who has a Raspberry Pi? Okay, excellent. Yes, who has more than one Raspberry Pi? Good. What I want to do with this session is really talk about how you can use the Raspberry Pi with Java. So that's really the idea, is to talk about Java on the Raspberry Pi and some of the interesting things you can do with Java and a Raspberry Pi. So I have some demonstrations which I will show you at the end. Now, being an Oracle employee, the first slide that I have to put up is the mandatory legal slide, which says don't base any purchasing decisions on what I'm about to tell you. Now, I think that doesn't apply to the Lego, but just bear in mind that we're not committing to any products based around the Lego or Raspberry Pi. Anyway, you've had long enough to read that. In terms of the agenda, what I'm going to do is I want to talk through a little bit about the basics of the Raspberry Pi and where the Raspberry Pi came from. The fact that all of you have heard about the Raspberry Pi is good. It's worth just spending a few minutes talking about the history of it and how it came to be, because it's quite interesting. I want to talk a little bit about ARM processors, because that is the heart of the Raspberry Pi, and talk a little bit about specifically how that makes a difference in terms of the Raspberry Pi itself. Then we'll talk about Java on ARM processors and some of the things that we've done as Oracle to make the Java on the Raspberry Pi work in a more efficient and better way. And then I'll spend probably most of the session talking about how you use Java with the Raspberry Pi, so the different kind of aspects that you can work with. And then at the end, as I say, I'll show you some demos of Java and the Raspberry Pi working together. And hopefully they will all work. Sometimes I have less luck than others with demos. So really start with the Raspberry Pi. This is a couple of pictures of the Raspberry Pi, and this shows the sort of, on the left-hand side, that's for the real sort of cognoscenti amongst you, you will recognize this as being the early release of the board, and the one on the right is the later release. This is the more, the one that you get nowadays. There's not a whole lot of difference between the two. Basically, this one has a couple of mounting holes, which is very handy for certain applications. The color of the socket is blue rather than black. Doesn't make a whole lot of difference. But internally, there's some very minor differences. Basically, the earlier one only had 256 megabytes of memory. The current one has 512 megabytes of memory. And there's one or two other minor differences that I will highlight as we go through. But this is essentially what we're dealing with. A small computer in the single board format. And it is literally, as you know, you can see here, there's one of them. It's about the same size as a packet of cigarettes. So where did the Raspberry Pi come from? A long time ago, way back in the 1980s, there was a thing called Micro Live on the BBC. Does anybody remember that? Oh, good. Okay, a couple of people. And out of that came the BBC Micro. Anybody have had a BBC Micro? Okay, the same. Oh, good. Okay. Now, what the BBC wanted to do with this was a very noble goal that they had, which was to educate people about computing. Because remember, this was about 1981, and this was before the IBM PC had even been launched. This was back in the days when personal computing was basically a Commodore PET. Anybody remember those? Or a TRS-80. Good. Okay. Classic stuff. Yeah. So what they did was they wanted to put on a program that would teach people about computers and teach people about programming. And so part of that was to develop a computer that people could buy and then use as with this program. Now, more recently, certainly in the UK, what has happened is that a number of people have got together and they have looked at the way that we teach children in school about computer science. And what we have is ICT. So if anybody's got children, you will know about ICT. ICT is information and communication technology. At least I think it is. And so I have a son who goes to school. He's 7, and he gets to do ICT, which basically means knowing how to use Word or how to use, web pages and things like that. But as you get older, they don't really teach you much more. It's still about using PowerPoint and using Word, and if you're really lucky, you get to learn about this programming language called HTML. which is not a programming language. So a lot of people were concerned about the fact that children coming out of secondary school into universities didn't really know anything about computers. They knew how to use them, they knew how to use game boxes, they knew how to use the iPad and things like that, but they didn't really understand how these things worked and how to program them. So a number of academics got together and they wanted to create a project that would change the way we teach computer science at school. And they wanted to get children more interested in the workings of computers, more interested in how you actually program computers. And out of that came the Raspberry Pi Foundation. And they spent several years putting together the designs for the Raspberry Pi board. So the ultimate goal of the Raspberry Pi is to get people interested in computer science again. It's been around for a little while now, so officially launched on February the 29th in 2012, last year, and the production run was initially 10,000 boards. So they thought, right, we'll be lucky, we'll sell 10,000 boards, that's how many they have made. Now, there are two companies in the UK who they signed up to do distribution of the Raspberry Pi. It's RS and Farnell. And if you know anything about buying electronic components, you know that RS and Farnell are very, very big companies. They sell electronic components to an enormous number of people, and they shift an enormous number of components. But on that day, from about 6 o'clock in the morning, when they launched this thing, the websites were literally brought to their knees. It was like a distributed denial of service attack by customers who wanted to buy these things, and they literally ground the websites to a halt. And RS actually reckoned that they had over 100,000 pre-orders in one day for the Raspberry Pi. So it is proving to be very, very popular. And they reckon that current production is about 4,000 boards a day. They now shifted the production of them from China, which is where they were initially manufactured, and they're now building them in Wales, in the Sony plant in South Wales. Yes. And they reckon over 1 million of these boards have been sold now. And I would actually say that probably more of the boards have been sold to people who are not at school than have been sold to people who go to school. But it is still the goal of the Raspberry Pi Foundation. We're actually working with them in terms of looking at how to get more Java into education and that sort of thing. So that's really the goals behind the Raspberry Pi. Now, if we look at what the Raspberry Pi actually is from a technical perspective, what you've got is an ARM CPU. Now, it's a single on-chip package, and it's a Broadcom package that they've developed. It has an ARM 11 core, which runs at 700 megahertz. So it's fairly low speed compared to your average desktop or your average laptop. However, what they have now said is that you can overclock the Raspberry Pi up to 1 gigahertz without breaking the warranty. And you can actually go a little bit further than that, but you would invalidate the warranty if you found that it stopped working. I typically run mine at 900 megahertz, and I've not had any problems with stability or the system not working in the way that I expect it to. Memory, as I said, they initially had 256 megabytes of memory. Now it's got 512 megabytes of memory. So again, it's a small amount of memory compared to what you see in a typical desktop or laptop machine today. What you've really got there is a PC from the mid-1990s in terms of the processing power and the memory. Actually, it's got a lot more memory than a PC from the mid-1990s, but processing power is about the same. Storage. In order to keep the price down, obviously they didn't want to have the idea of a hard disk connected to it and that sort of thing. So they've added an SD card reader, and you can plug in an SD card and you can use that as your storage. You can put the distribution on there, you can read and you can write from it, and that works very well. I mean, it's not necessarily as fast writing as a hard disk, but if you use one of the higher spec cards, you can get pretty decent speed out of that, and it's very cheap because you only need a 2 gigabyte card, which is literally less than £5 for one of those things nowadays. The other really nice thing about this is it's got some really interesting input and output on it. So it's got the standard sort of things you'd expect. It's got USB ports, it's got an Ethernet port. It has audio out only, so there's no audio in. You can't plug a microphone into the 3.5mm socket, but if you wanted to use a microphone, you can use one of the USB ports and go through that route. For a monitor, again, to keep the price down, rather than having people buy a separate monitor for this, they said, well, let's use an HDMI output, and then you can plug it into a TV. same as the ideas behind computing many, many years ago. It also has composite video, so if you want to plug it into a composite input, you can do that as well. And then the really nice bit is there's a row of header pins on the board which allow you to access the sort of lower level interfacing functionality. So there's things like GPIO, which is general purpose I/O, there's UART for serial communication, there's SPI and I2C, which are well-used communication protocols or interfaces for low-level types of devices like sensors and things like that. So it's got a lot of potential, a lot of capabilities. And as I say, what they want to do is get people excited about computer science, get these sort of things into the hands of children so they can experiment with it and do interesting things with it. Yep, sure. Where did the Raspberry Pi come? Now, I'm trying to think whether it was, I can't remember off the top of my head. It was something to do with the fact that there was it because there used to be a Tangerine computer, I remember that. But I'd have to look it up. I can't remember the exact details of why they called it the Raspberry Pi. But yeah, it seems to be a popular name. So let's talk about the ARM architecture. So here we're going to get into a brief but interesting history lesson. So if we go back to when the BBC Micro came out, what you had there was this nice little machine which had a 6502 processor in it. Now this is a lovely processor. It's 8 bits. It has a flat memory model, has a simple instruction set, and is a very easy way to learn assembler programming. But the problem is that the people who actually manufactured the BBC Micro was a company called Acorn. And Acorn decided that what they wanted to do is they wanted to move into the next phase of the computer revolution, and they wanted to get computers into business as well as into education. And they looked at the 6502 and they thought, well, it's a nice processor, but it's not powerful enough to run the kind of business applications that we want to do. So they thought, right, we need a different processor, one that's better suited to business applications. Now, most people at that point would have looked around and they would have said, what's available? What can we get from, at that time, it would have been somebody like Zilog or Intel or whoever. But no, these people were at Cambridge, and so they looked around and they thought, it can't be that hard. We'll build our own chip. So that's what they set about doing. One of the things they looked at was the RISC project, which was being run at Berkeley University in California at the time. What that project did was it looked at the Unix kernel, that's the Unix kernel, not the Linux kernel, and they figured that only about 30% of the instructions which were available in a Motorola 68000 processor were being used in the Unix kernel. And that's a fairly complex piece of code, but it was only using 30% of the instructions. So why have all these extra instructions in the design of the processor? Why not reduce the number of instructions and make the processor lighter weight and have the ability to do things faster? Now, as an aside, does anybody know why the Motorola 68000 was called the 68000? No. Okay, it's because that's how many transistors it had in it. So it's just as a completely useless aside. But the idea behind this was, because this is back in the 1990s, processing power meant reducing complexity. So they wanted to reduce the complexity of the processor to make it run faster. And that's what they did. They put more registers in, less instructions. And out of that came the idea of the reduced instruction set computing. One of those was actually the SPARC processor, which ended up at Sun and now at Oracle. And out of that came the Acorn RISC machine, or for short, ARM. I suppose it really should be Ariscum rather than ARM, but that's what it became, the Acorn RISC machine. That had 32-bit data bus, it had 26-bit address space, and 27 registers. And the first of those was the Acorn Archimedes. Anybody remember the Acorn Archimedes? Same people, good. And what they decided, after a while, they decided to spin off the chip manufacturing business, and that became Advanced RISC Machines, which is now called ARM. That's where ARM came from. In terms of the features of the ARM processor, it is a 32-bit RISC architecture. And what this accounts for is about 75% of all the embedded 32-bit CPUs that are made today. And that's a lot, because if you think about phones, if you think about tablets, if you think about embedded devices, there's an awful lot of these things being manufactured. These numbers are actually quite out of date now. And they reckon that last year, which I think is actually the year before, no, it's still last year, about 8 billion chips were manufactured with the ARM design. And there's well over 35 billion ARM processors in the world today. 0 of them were actually manufactured by ARM, because ARM are all about design. They then sell the designs to other people, people like Freescale, people like Texas Instruments, people like Qualcomm, who then take those designs, put them into the chip that they want to actually manufacture, and then they manufacture the chips for other people. Same with Apple. Apple take the ARM design, they use it for their processors as well. What they actually produce is 2 things. There's an abstract architecture, and then there's a microprocessor core design. So without going into all the details of how you actually design processors, these are the things that you need in order to create a processor. And so what you've got is the Raspberry Pi using an ARM 11 architecture with an ARM v6 instruction set. So it doesn't make a huge difference to what you do with it, but it's just worth knowing that that's what's at the heart of the Raspberry Pi. And one of the really good things about the ARM designs is that they are very low power. They're designed for mobile devices, and so the power consumption is very low compared to the typical desktop or laptop type of processor. What this means is that from the Raspberry Pi perspective, you can power the Raspberry Pi off a USB port, as long as you can actually get 750 milliamps, which is admittedly above the USB specification, but a lot of ports will actually give you more than 500 milliamps, or you can buy an adapter which will give you more than 500 milliamps without any problem, and they're very cheap. So again, this was designed to reduce the cost of running a Raspberry Pi. You don't have to have a big, complicated 5-volt, 12-volt power supply and so on. And the other thing is, of course, because it uses so much less power, it also generates a lot less heat. So for example, this one here that I've had on for the last sort of half an hour or so, if I put my finger on the processor, it's like I can just about detect that it's warm, but it's not going to burn my finger. I don't need a heat sink on there to actually keep it cool. So these are all good things for the idea of having these things generally available and making them easy to use. From the point of view of the ARM technology at the moment, there's 3 different versions that are available. ARM v6 is actually the older one and is tending to sort of die out. So there's ARM 11, and then there's ARM Cortex-M, which is for mobile devices. That's the ARM v6 instruction set. ARM v7 is the kind of current set of designs that they have. There's Cortex-A for applications, Cortex-M is mobile, and Cortex-R for real-time. And those are just different designs that they have for different types of use for this kind of technology. ARM v8 is announced, and they're starting to sort of get some chips designed with that, but we're still not seeing them generally available. And the big thing about that is it's going to have 64-bit addressing support, so it's going to go up to the next level. And a lot of people are actually looking at ARM processors as a suitable thing for enterprise applications and running them in data centers because of the low power consumption and the low heat that they generate. So it actually makes it a lot more cost effective in data centers. So there's some interesting things around ARM technology that's going on. Talking about Java on the ARM and the Raspberry Pi, some of the things we had to do to kind of adapt Java for that. The big one was floating point, because if you look at the ARM v6 instruction set and the way that the architecture works, it doesn't mandate the idea of hardware floating point. Most processors deal with integers very happily because they're round numbers, therefore you can convert them into binary representations very simply. For floating point numbers, you have a choice of either doing it in a library where you have to take the floating point representations, convert it into integers, do the arithmetic using the processor and then convert it back again, or you have to have some kind of hardware which is specially designed for processing floating point numbers and doing the arithmetic. So the ARM v6 architecture doesn't support a floating point processor by default, but the Raspberry Pi does have one built in. So their architecture does have a floating point processor. What that meant for us was that we had to recompile everything to make sure that we used the floating point processor to get the best possible performance out of it. And certainly if you do anything that's sort of graphics oriented, then you do notice the difference between using hard and soft floating point. It took them a while to get the Linux distro to use the hard floating point, but that was fixed it's probably about 6 months ago, 8 months ago now. So there's a Raspbian distro, which is built on Debian, compiled specifically for the Raspberry Pi, makes use of the hard floating point and so on. And then Oracle also had to adapt or recompile the Java runtime and the Java development kit so that it would use the hard floating point as well. What we did fairly recently, in fact, literally last month, was we released a supported version of Java SE 7, which is now included by default in the Raspbian distro. When you download the Raspbian distro, you get Java from Oracle rather than the OpenJDK implementation, which is compiled for hard floating point by default. You can also get Java SE 8 as an early access. So if you want to use Lambda expressions and nice things like that, then you can. That also includes JavaFX. The Java SE 7 version doesn't include JavaFX. Java SE 8 does include JavaFX. And that way you can do graphical things, which I'm going to show you a demonstration of in a little bit. So that was basically the thing that we had to do there, was recompile stuff. There are a few other things that you can look at in terms of improving the efficiency of both the Linux distribution and Java on top of the standard build, because a lot of the ARM technologies are sort of optional bits that you can get inside there. So there's things like digital signal processing enhancements. Not much use for us in the Java side of things. It's really for how you make mobile phone calls, that kind of thing. There's a thing called Giselle, which is actually a bytecode instruction processor built into silicon. So you'd think, oh, that's great, so all we have to do is throw our bytecodes at this silicon on the chip and we'll get superb performance out of it. But it turns out that it's actually not that good an implementation of the bytecode processor. And so by running the JVM, you actually get better performance because it can do all sorts of interesting things like adaptive compilation, and it can do aggressive method inlining and stuff like that, which gives it a better performance profile. There's some other things around reducing the size of applications. So there's this thing called Thumb2 and Thumb EE, which basically takes instructions and says, well, if you've got a number of operands that go with an instruction, you can say, I'm always going to use the same operand, and you can forget about that operand and reduce the size of the instruction. It's fairly sort of esoteric, I would say, from the point of view of Java. Floating point we already talked about. Neon is kind of like the same as the SSE instructions in the Intel processor, if you know about those. It's all to do with sort of multimedia and processing those kinds of things. And then there's also a couple of things around security, which we're actively looking at the moment. So there's this idea of trust zones, where you can have both the kernel mode and the user mode executing in separate zones on the processor, and it's the processor that does the isolation for you. One of the other things we've done is, because we at Oracle really like the Raspberry Pi, is to look at how we can make other parts of Java available. So there is the idea of Java ME embedded, which is the micro edition. And this is really designed for types of applications which run in potentially even less than 1 megabyte of memory. So if you're interested in developing embedded applications and you want to try out Java ME embedded, the Raspberry Pi is a great way of doing that because it's cheap. You can try out your application, you can make sure it works, and then move it on to the platform that you want to deploy it on. One of the other nice things about the ME embedded implementation is it has this thing called the Device Access API. There's a library in there which allows you to talk to GPIO, SPI, I2C, UART, and so on directly from a standard library that's part of the Java environment. We'll talk a bit more about that in a moment. So let's talk about using Java on the Raspberry Pi. And what are the sorts of things you can do with it, and how do you do them? So when I first sort of started looking at the Raspberry Pi, there was a number of areas that I thought would be interesting to look at. And one of those was sound, because I thought, oh, let's get the Raspberry Pi to talk, let's get the Raspberry Pi to make interesting sounds and things like that. And I've had somewhat variable success with that. There's one of the first problems was that the early distributions didn't have the sound drivers included by default, so you then had to install those separately. That problem's gone away because the default distributions now have the sound drivers, and that's all installed by default. There is a Java Sound API, and there's a couple of things you have to do in order to make that work. One is you have to add the audio group to your users list of groups so that it has access to the audio output. And then you also have to make sure that if you want to use the MIDI interface, then you have to do modprobe snd_pcm_oss in order to create the /dev/dsp device, which is what's used by the MIDI controller in order to make sound from the Java Sound API. So what I've found is that some bits work and others not so much. I haven't really spent a lot of time looking at this because I had various other things that I wanted to work on. But I found that if you had a WAV file, you could play that with the Java Sound API pretty easily. It worked, not much problem, as long as you had the right format of the WAV file in terms of the bit rate and so on, then it all worked. The MIDI interface was unbelievably slow. So what I mean by unbelievably slow was I was experimenting with this and I wrote some code. And every time I ran it, it would sort of go through my code and it would get to the point where it was opening the MIDI interface and trying to access it, and it would just stop. And so, I did the typical debugging thing of putting print statements in and finding exactly where it got to in my code, and then it would stop. And I just couldn't figure out why it wasn't accessing this. And I was trying things like strace, and I was trying to debug it from underneath and figure out what was going on, not getting anywhere. And at one point, I started running this piece of code, and then the phone rang or something, and I had to go and do something else. And I'm sitting there, working on something, and all of a sudden, sound starts coming out of the speakers. And it had taken literally 3 minutes for it to open the MIDI interface, and then it started making sound. So I have no idea why that does that, but like I said, I've had fairly mixed success with sound. The other thing I thought was, okay, let's use the free TTS, which is text-to-speech, and get that to work with the Raspberry Pi. And because that basically relies on some of the stuff above, if you use a limited domain voice, which means it's a predefined set of words, then that works quite well. So if you want it to tell the time, that will work. But if you want to use an unlimited domain for the vocabulary, which uses the MIDI interface, then you run into the same problem of trying to use the MIDI interface that you do for any other sound. So, like I say, with sound, I've had fairly mixed results in terms of getting that working. JavaFX. So what we wanted to do there was to make sure that JavaFX would run well on the Raspberry Pi. And what we've had to do there is, because JavaFX uses a thing called the Prism graphics engine, and what we did there was to make sure that JavaFX could take advantage of the hardware acceleration that was available on different platforms. So if you're running Windows, it'll use Direct3D. If you're using Mac or Linux, it'll use OpenGL, because those things use hardware acceleration underneath and they work very well. So with the Raspberry Pi, we actually had to port the Prism graphics engine, make it use OpenGL with Linux, and then recompile it to run on the Raspberry Pi with the ARM architecture. One of the nice things about the Raspberry Pi is that although the processor itself is fairly slow and is not like a typical desktop, the graphics processing in it is actually quite powerful, even by today's standards. So it has a thing called a Video Core 4 GPU, and it can certainly run at sort of HDMI type resolutions, and it can do 720p, 1440p without any problem. So a lot of people use Raspberry Pis as media servers because you can drive a full TV with high resolution on it without any problem. JavaFX, having done that, one of the things we did originally was we did support X11. So you could start up the desktop on the Raspberry Pi, and then you could run JavaFX applications on there in separate windows. But we found that was actually really bad in terms of performance, and the analysis we did showed that it just wasn't going to be something we could solve easily because it was more to do with the X11 implementation underneath. And so we decided that rather than supporting that, which didn't make sense from what we were trying to do, we would only support JavaFX using the frame buffer directly. So at the moment, you can only use the frame buffer directly. Again, I'll show you an example of that later on. A couple of things that are not supported. So we don't support media playback, so you can't run videos on the Raspberry Pi using JavaFX at the moment. That is something we might get around to in a couple of months after JavaFX or JavaFX 8 comes out. Web engine, web view is really about size, because we would need to bring in the WebKit rendering engine, which is pretty big. And so again, we could do that. It's not technically difficult. It's just finding the engineering time to do it. And there are a few things around I/O that need a little bit of work with JavaFX. Because it's early access and JavaFX 8, there's still some things that they're ironing out, some of the details. So for example, I had a gamepad connected to the Raspberry Pi, and I was trying to use it with JavaFX, but for some reason it just wouldn't actually pick up the events. We'll come back to that again later on when I talk about something else. So other things you can do. There is a serial port, the UART, that's available on the Raspberry Pi. And so what you can do is you can actually start getting into electronics, and you can build a simple interface, because the UART runs at TTL voltages. So that's sort of 3.3 volts. And if you want to use RS-232, that runs at 12 volts. So if you want to plug in some sort of RS-232 type of device, should you have something like a monitor and something like that, then you could do that. But you need something to convert between the two voltage levels. And there's this nice chip called the MAX 3232, which will do that for you. So it's very simple. I actually built one of these quite easily. It's literally one chip and a few capacitors, and that's all you need to do. Once you've done that, you can then get the serial console to display on your machine. So if you want to see the messages coming out from the boot system as it goes through the boot sequence, you can see those messages. If you want to use it for something other than seeing the boot messages, then you need to turn off the serial port, and there's a couple of things you can do for that. Which brings me to my next bit. So I wanted to get the Raspberry Pi to talk, and so rather than using the free TTS and trying to use the Java Sound API, I had this little board which I bought quite a long time ago, which is the SPO3 text-to-speech board, and you can drive that with a serial interface. And so what I did was I connected that up to a serial interface, connected it to the Raspberry Pi. And then obviously you have to disable the console output, because otherwise when you start booting up, all of the boot messages get read by the sound, by the speech card, which can get a bit boring after a while. So you need to edit a couple of files. One is the etc initab, and I've got to say that really took me back in memory. Editing etc initab and remembering the getty process that you kick off when you want to have something running on the console. So you need to comment out the dev tty ama0 line to stop it from creating a login prompt on the console. And then if you edit the boot command line.txt and remove the console and kgdboc references, that will stop the boot messages coming out to the console as well. From the point of view of driving this, it was fairly straightforward. It's just a 38,400 baud. Going back in history, 8 bits, 2 stop bits, no parity, and then there's a nice simple protocol in terms of the way you send bytes to it, and then it's all easy to make it talk, which we'll see later on. USB peripherals, if you want to access those from Java, there's a couple of ways you can do that. One is if it appears to be like a serial device, then it's quite straightforward, because you get something like /dev/tty USB 0, and then you communicate with it as if it was a serial device. You send sequences of bytes, you get sequences of bytes back. If you need more complicated things, then installing the libusb-1.0-0-dev package is a good idea, because that gives you the necessary library code you need to access USB devices directly. So if you want to use serial devices and talk to them directly, then there's a nice little package which is really an implementation of the Java COM API, which goes way back into like the last century, in fact. And so you can install the RxTX package, which is a Java implementation that allows you to do that. One of the things I found with that is that by default, the RxTX package will only use devices which are /dev/tty S something. And it assumes that anything that is a serial port, and anything else is not a serial port. So there is a way around that, and so you need to set properties in order to say, okay, I want to use something other than /dev/ttys, and you say, in this case, I want to use /dev/tty USB 0 or tty AMA 0, and that will configure the system so you can then talk to that directly. This was one of the devices that I connected to the Raspberry Pi a little while ago. I didn't bring this one in with me because it's a bit heavy and a bit bulky, and I already had a whole load of stuff. And trying to get through the morning rush hour on the tube wasn't going to be a lot of fun with a robot arm. So I got this from Maplin. It was about just over 20 quid, I think. And it comes with a USB interface, so that was nice. Had a Windows driver, but there's no Linux driver by default. But it did get recognized by the Linux distribution on the Raspberry Pi. So I could see some devices. That was good. So then I wrote some JNI code and got it to actually work with that, and made it do some things in terms of being able to move the robot arm and stuff like that. So that was all kind of interesting. Just talking a little bit more about that, because this is one of the things that you can come up against, is that sometimes you do need to drop down into native C code in order to do low-level interfacing, and then you need to use JNI. Who's used JNI? Okay, reasonable number of people. Who likes JNI? One person. You like JNI. Well, the good news is, for those of you who don't like JNI, like me, is that hopefully in JDK 9 we are going to rewrite JNI. And what I thought was really funny was that I was talking to one of the engineers who was kind of responsible for this area. And I said, you know, JNI is a real pain to use. And he said, oh, yes, it was designed that way. I was like, what? It was designed to discourage people from using it, which I don't think is necessarily the right approach to take when designing something. But anyway, so what you can do is you can create a set of native code with a set of native functions, and then you can map those using JNI into Java methods, and then you can call those as appropriate. And there's a conversion between native types and the Java types as appropriate. Yeah, so what I ended up with was a nice sort of simple thing. If I wanted to move different parts of the robot arm, I could just call, you know, move this particular gripper and then sleep for a certain amount of time, and that would control how far the motor moved. I don't know if anybody saw the keynote demo that was done at Java 1 this year, where they had the robot that played chess. That was really interesting because I talked to Jasper about that, who built that, and he said that they hadn't done it using an arm which actually had position sensors on it. So it was all done by timing. And if you've ever tried doing that for a complicated system, the margin of error doesn't have to be very high before you get way out of line after only a small amount of time. So different ways of approaching different kind of problems. Another thing I did, as I said, I connected a Gamepad controller to the Raspberry Pi to see if I could do some interesting things with that. There's Linux support by default straight out of the packet. It doesn't cause too much of a problem. There's some devices that get created in /dev/input. And then there's this kind of, again, rather antique API from Java, not an Oracle API, it's a third-party API called JInput. And what that allows you to do is to basically talk to a gamepad controller, and you can get events when buttons are pressed, you can get events when the joysticks are moved and things like that. So the first thing I had to do was recompile the code on the Raspberry Pi because it needs some native code, some JNI stuff. And there were a couple of minor things I had to change, one of which is that because there was some weirdness in Linux where they'd removed one of the definitions in a file, so I had to kind of comment that out and get around that. And then a weirdness where when I created an SO file called libjinput-linux.so, the only way I could get it to work, and again this was like through basically doing strace to figure out what it was trying to do underneath, was to rename to libjinput-linux64.so, even though it's a 32-bit processor, so go figure. But anyway, I eventually got it working, which was the important thing. And then the one thing is that you need to have root access, or you need to configure some UDEV rules. So anybody here used UDEV rules on Linux? Oh, okay, nobody, good. Don't try. It's just like I spent ages trying to, all I wanted to do was do effectively a chmod to change the permissions on these files. Could not get it to work at all. So after about 2 hours, I gave up and just decided that I would use root instead. Again, from a programming point of view, what I did was I then sort of wrote a small library on top of the JInput library just to give me sort of a high-level function. So I could register listeners for particular things and then say, okay, if I press button 1, I want to do this. If the joystick is moved this way, then I want to do that. So yeah, let's just kind of move on from that. That's a bit more of the code. So it's just the listener pattern, and yeah, just does different things. So what I did was I linked the gamepad controller up to the robot arm so I could control the robot arm with the gamepad controller and make it move around. So the next thing I thought I'd try was mind control. So there's a company called Mindwave who have produced what looks like a sort of headphones, but rather than actually playing music into your ears, it actually monitors your EEG activity. And it's quite interesting because it's a dry sensor. Typically, if you want to monitor EEG activity, then you have to have a lot of sensors all over your head and you have to have this conductive gel, so it gets very messy. But they use dry sensors, and there's 2 sensors, one of which goes on your forehead, one of which goes on your ear. And then they can monitor the electrical activity of your brain from that. And then that just sends a sort of Bluetooth communication to a dongle, which you can plug into a USB port. The USB port then communicates in a serial fashion, so you just send a sequence of bytes, you read a sequence of bytes back. And then I wrote a custom library, which just sat on top of that and read the information back and forth to find out what my brain was doing. Well, in theory. We'll see how well that works in practice. Okay, like I say, there are a bunch of these pins on the Raspberry Pi, and this is the layout from the Rev 1 board. And so you can see that there's different colored ones which I've marked. So the one, you've got 5 volts, you've got ground, there's a 3.3 volts as well. The blue ones are for I2C, the orange ones are for the UART, so you get the serial communication. Green ones are the GPIO pins. Some of them are shared, so if you want to use more GPIO pins, you can, you just don't use the UART, so on. And then there's SPI on the purple ones. So that was the Rev 1 board. The Rev 2 board, see if you can spot the differences. Okay, so what they did was they added more ground pins, which is actually very good because those are the things you actually do need from more of than one of. And for some bizarre reason, they changed one of the pins to be a different GPIO number. No idea why, doesn't really make any difference, but it's just worth knowing that that's what they did. When it comes to using those GPIO pins, things get a little bit tricky. So first thing I did was I actually tried writing some native code to communicate with the GPIO pins and do all sorts of stuff like this. So you end up with this kind of magic incantations, which requires malloc and doing memory mapping and stuff like that. Fortunately, I didn't have to figure out all these values. Somebody else had done it for me. I just wrote a bit of code around it. But as you can see, it gets really kind of involved in terms of bit twiddling and so on. If you want to set GPIO pins high or low or read the values, it's all sort of bit twiddling and general nastiness. So there are easier ways of doing it. This was basically what I used to write some things that I could move a motor on using my Lego stuff. But again, you needed access to /dev/mem, which needed root access. So yeah, okay, not the best way of doing things. So then some other people came along and they wrote a thing called Pi4j. And this is a very nice piece of code because it provides a library which hides all of that nastiness from you. So there's a nice way of doing this, this simple API that allows you to control GPIO, I2C, SPI, and so on. Still need root access, but it makes life a whole lot simpler. It's still under development. Current version is 0.0.0.4, so some way off the 1.0 release, but it does work pretty well. I've not found any problems with actually trying to use the different bits that I wanted to use. In terms of using GPIO, this was an example that I came up with because I wanted to control a Lego motor. And the problem with the Lego motor is the Lego motor runs at 9 volts. And obviously you've got 3.3 volts on the Raspberry Pi, so there's a mismatch there. So you need what's called an H-bridge. And again, there's a nice simple chip that you can get. Doing electronics nowadays is actually quite simple. Don't even need any other external components. If you get the right version of this, you get the L293D, because that has all the diodes internally, otherwise you have to put them externally. But if you get the L293D, that gives you a dual H-bridge, and you can wire up 2 GPIO pins to control the motor. So one says to go clockwise, one says to go anti-clockwise, and so you just put one pin high, one pin low, and then you can drive the motor in whichever direction. Both pins low, it stops, both pins high, not very good. So that was quite simple. Again, using Py4J meant that was easy. This is the latest thing that I've been working on, and I did a session on this at Java 1. What I've done is I've connected the Raspberry Pi to my car. So there is a thing called an Elm 327, which is a little box that you can buy from eBay for a few pounds. And what that does, it plugs into the service port on your car. And then it becomes like a little Wi-Fi hotspot, which you can connect your Wi-Fi to, and you can communicate with the car. And so you can find out what the different values of things like where the throttle is. You can find out the things like what the engine temperature is and what the engine load is. And if you want to be really daring, you can actually then also communicate through what's called the CAN bus. The CAN bus is the sort of more proprietary technology that people use in cars nowadays because the wiring is so complicated. So if you can decode the CAN bus signals, you can actually find out all sorts of weird things like what angle the steering wheel's at, or where the electric window is in terms of what percentage it is up or down. And then you can then start writing things as well as reading things. So you can say, I want to move the electric window from there to there, and you can send a signal. I've not been brave enough to do that yet, but I'm kind of looking at different ways of doing things. So what I ended up building here was an interface which had a touch screen which sat on top of the dashboard, and then that would allow you to display different values you can see there. And I also had in there an accelerometer which I connected to the Raspberry Pi. So I could measure the acceleration of the car, take the information from the internal workings of the car, and then you could create values of like the torque and the horsepower as the car's actually running. So that was kind of interesting to do that. And then that kind of brings us to the touch screen, because again, good old eBay, you can find these things on eBay. And what I wanted to do was to use this as a touch screen. And what I found was that when I connected it to the Raspberry Pi, it just connects via HDMI, it would, if I started up the X server and had the desktop on there, it would work fine, no problem at all. But if I started JavaFX, it wouldn't recognize any touch events. And I couldn't work out why this was. So I started working with the engineers in the JavaFX team. And it turned out that the device is recognized, and it's an eGalax Inc. device, but it creates 2 devices in /dev input. So there's event 0 and event 1. And JavaFX was saying, well, we'll take the events from event 0. But for some reason, all the events go to event 1, which is not very helpful. So it didn't work. So I talked to the engineers, and they said, well, we could do a special build of JavaFX for you. So it takes the events from event 1. And I just happened to be sitting there one day, and I thought, well, hang on, I can solve that a different way. So what I did was I said, OK, well, let's write a little script as the system starts up. We'll delete event 0, and then we'll recreate event 0 as the same major and minor device numbers as event 1. So then event 0 is still getting the same data from event 1. And lo and behold, it all worked. So that was kind of useful. But it shows you some of the issues that you have to work around with this. So just to conclude, before we go into the demo section, the Raspberry Pi is a very cool and cheap computer. So it's a great piece of kit for actually learning about how to program things, and you can do all sorts of interesting things. Because it is so cheap, you can kind of throw it at different applications, and you don't have to think, oh, I'm investing a lot of money in this. So for example, one of the other projects I'm working on at the moment is a weather station. So I've got a set of sensors that I've got on my garden shed, and I've got a Raspberry Pi in my garden shed. And I'm trying desperately to make this work in terms of the Wi-Fi connection between the shed and my house. I won't go into it now, but I've spent ages trying to make this work, and there are all sorts of problems that are nothing to do with Java and nothing to do really with the Raspberry Pi, to be honest. But it is a good platform for doing things like that. So there's all sorts of different applications you can use for it. Place to go for more information, obviously java.oracle.com. There's also on oracle.com tech network, there's an embedded part there you can do find more information. Eben Upton, who was one of the founders of the Raspberry Pi Foundation, has written a guide to this. There's a lot of useful information in there. And if you want forums where people discuss all manner of things related to the Raspberry Pi, the raspberrypi.org website. And I've got my own blog where I've covered a lot of the things I've done with the demos in terms of the blogs that I've written as well. So let's just spend a few minutes doing some demos and see where we go with that. So let me see. Right. So first thing I'll show you actually is just the get the sound card, or not the sound card, the speech system to work. So if I just run, let me just make sure I'm still connected. Yes, I am. So hopefully.
Hello from the talking Raspberry Pi.
There we go. So that's just a simple use of a pre-recorded, or not pre-recorded, but predefined piece of speech that we can use from that. But we can also get it to basically say whatever we want to. So
hello, London.
So you can type in whatever you want, and you can get it to be as rude as you like. But I mean, the quality is not fantastic, but it was very cheap, and it is quite old. But again, it just shows how you can use the serial interface. You can connect different things and have stuff like that work. So the next thing was the idea of using the Lego motor. So let me just check that. I'll run a little test application. So that's just going to move the Lego motor, hopefully. Oh, I'll tell you what it's not going to do. Aha. I need to connect the battery. Otherwise, it won't do anything. Right, try that again. It'll work now. Yes, okay, good. Right, so like I say, that's just using a simple GPIO communication through an H-bridge and then using timings to determine how far it moves. So what I can then do is, actually, let me just put this on. Now, I know it says it's a dry sensor, but it does actually work a lot better if you just make it a little bit wet. So I get to wear some great things in my presentations. So hopefully that's made a good enough signal. Now I have to remember to turn that on. So what I should do now, hopefully, is get the signal. Yep, good, okay. So what we're seeing now is we're seeing, you might just be able to see, there's a series of values that are coming back from there. Now you can get raw values in terms of your alpha waves, beta waves, gamma waves, and so on. But what they also do is they give you a sort of processed version of that, which they equate to how much you're concentrating and how much you're relaxed. So obviously orthogonal values. So what I then thought was, okay, let's take the output from this and feed it into the Lego motor. Hopefully if this stays on, there we go. Let's see whether we can make this work. So in theory, if we get a signal from this, yep, there we go. So what it's doing now is taking my attention value and it's using it to determine where the position of the arm on the Lego goes. So in theory, if I concentrate, it should go one way, and if I try and relax, it should go the other way. Doing that while you're presenting is not actually that easy, and it does kind of it all seems to be a bit random. I have to say, I've got a colleague of mine, and she can actually do this quite well. She actually can control whether it goes up or down, because she seems to have better control over her mind than I do. So that was that demo. Now, the other thing I want to show you just quickly is the car system. Oh, no. So let me just switch over to this. Now, it's going to be a little bit difficult for everybody to see because it's going to run on this display. But what I'm going to do is, hopefully that'll come up with something. Right, if I just switch to, because what I did was, I said, okay, I obviously can't bring my car with me. So what I did was I took the system in my car and I went for a drive with the car. And as I was using the system, I got it to dump all the data to a file. so that I could then play back the data through the system in a sort of simulation mode. So if I run this application here, that will just basically set up a server that listens for connections from here. And then if I run the application on here, hopefully what we'll see when it starts up, yeah, there we go, it's starting. It takes a few seconds to start up because there's a fair amount of stuff going on, but in a moment we will see a splash screen appear. Any moment now. Yeah, there we go. So that's the splash screen. And then what it's going to do is it's going to show you the values. And it's reading the values from the laptop as if it was communicating with the car. So I've basically simulated the data coming from the car. And then what I can do is I can switch between the screens. And I've got different values coming from there. So that's giving me the torque and the power output. And then using the accelerometer, I don't know if anybody watches Formula 1, and you get this kind of like display of the G-forces that the Formula 1 cars are experiencing. It's quite interesting to compare this because I was watching the Indian Grand Prix at the weekend, and they had Alonso, who had it was pulling about 4.5 G laterally. It never really goes beyond about 1 G. I've managed to get it to about 0.8, 0.9 G going around a corner, and about the same for acceleration and deceleration, but it's some way off being a Formula 1 car, I have to say. The other thing that you can do is you can monitor like the throttle position. So this is a historical thing. You can see where I actually wellied it there. And then also if you switch to that, that's giving the power output. So you can see where I hit the throttle and you can see the power went up. So that's really just like the idea of being able to see different values and, like I say, and then like an exit button. But that was really to sort of demonstrate that's using JavaFX with the Raspberry Pi, using the accelerometer and things like that. So I think I've run out of time. So I hope you enjoyed that. If you've got any questions, please come and see me at the end. And thank you very much.